So we'll like be a little bit working ahead in the notes as compared to what we're doing in the lab. And that will probably be true for every lab moving forward. Okie doke. So, starting a conversation on minerals, we're going to start off with this really brief overview of our most basic concept from chemistry, which is that matter exists in the universe and everything that we know is made up or has matter, or is matter. Matter is made of really small particles that are known as atoms. This is the smallest unit of matter that contains the properties of whatever element it is. The element is a pure chemical substance consisting of one type of atom. If you look at the periodic table, you're going to see all the known elements that we have listed there. Some are metallic, some are non, some have special properties. Some of them are minerals, some of them aren't. The smallest unit of a substance that has the properties of the substance would be our molecules, or rather that could be a combination of atoms. Minerals, they have a 5-part definition. They're naturally occurring crystal solids with a narrowly defined chemical composition, and we're going to go through their 5-part definition more in detail briefly. Minerals, when they combine together in an aggregate form, they create rocks. So rocks are naturally occurring aggregates of one or more mineral. So minerals and rocks often kind of get called by each other's names, but they are distinct things. So in this class, we're going to try really hard to mention minerals as minerals and call rocks rocks. When you do your lab on Monday, you're going to be asked to write a report, and in it, you should be calling them minerals, because everything we're going to work with on Monday is a mineral sample. It is not a rock. It is the ingredients that make rocks, but on its own, it's just a mineral. So, I said we're going to go through this 5-part definition. We're going to go through each one on its own slide, but in order to be considered a mineral, you have to meet all 5 of the following criteria. You are naturally occurring, inorganic, solid, have a definite crystal structure, and a definite chemical composition, which means you could be written as a chemical formula. So if you hit 4 of the 5, you're not a mineral. You're a mineraloid or mineral-like. But in order to be a mineral, you have to hit all 5. So what does it mean to be naturally occurring? Pretty straightforward. You're formed by natural geologic processes. You're not formed by man-made processes. You're formed just naturally in the earth. So for example, diamond is a mineral. Something like cubic zirconia is not considered a mineral because it's lab generated. Natural rubies are minerals. Technically, lab-created rubies would not be considered minerals because they don't hit that full definition. So technically they wouldn't be, but the boundaries I think are getting a little hazy now, especially with cubic zirconia used to be the diamond replacement like when I was young, but now we have actual lab manufactured diamonds that are real diamonds in every single essence, but they technically aren't naturally occurring, so probably wouldn't truly be a mineral, but it'd be impossible for you to distinguish them from a natural one, so it might be hard to say. But the boundaries are a little hazy, but that is sort of the rule that we abide by. Next part means generally inorganic. That's the second part of our definition. So this means that they are not produced by organic processes, meaning they don't come from living things. So substances like pearls or coal or amber are not considered minerals, even though they have a lot of properties of minerals, because they're made through living organisms. Pearls come from oysters, amber comes from trees, so these would not be considered minerals. However, again, as with all rules, there are exceptions. So some seashells, like a seashell is not a mineral, but there are some minerals that are comprised of like microscopic shells that are lithified together, and those are minerals. So again, it's a little bit hazy there. So we like to make rules and then have exceptions for them. So generally speaking, if you're made by an organic process, you're not considered a mineral. But there are some that are made from ocean-dwelling creatures that are considered minerals. A very famous one that we'll hear a lot about. This one is pretty straightforward. You have to be solid to be a mineral. If you exist in a liquid or vapor state, you're not a mineral. So that one's pretty straightforward. There's not really any exceptions to that. If you're solid, you could be a mineral. If you're liquid or vapor, you can't. Next one is having an orderly crystal structure. So minerals are comprised of atoms. Atoms are arranged into an orderly and repetitive pattern in a crystal system. And this is reflected in the shape that the crystal exhibits, which for a mineral is called its habit or its crystal shape. Obsidian and other naturally occurring glasses, they have an amorphous texture, so they lack this crystal structure, so they would not be considered minerals, even though they meet all of the other criteria. Something like opal has also an amorphous structure, so it's not technically considered a mineral. It's a mineraloid or mineral-like material, but not a true mineral. We're going to learn about some of the different crystal structures that exist, but this has to be organized in some way. And there's a little image to kind of show you what an organized crystal structure might look like. And then lastly, minerals have a definite chemical composition, which means that they can be expressed in a chemical formula. There is some variation in this. In certain minerals, there are elements that are very close to one another, so sometimes the elements will substitute out for one part of the chemical formula. But for the most part, they're going to have a specific chemical formula. So like, for example, a very common mineral is quartz. It's one of the most common minerals on Earth. We have a lot of it in New Jersey. And the chemical formula for quartz is SiO2. So if we see this, we know that's quartz. Another really famous mineral is calcite, and its chemical formula is CaCO3. It's also known as calcium carbonate, so that would be another one and how we can express it. And some of them are a little more complicated, but I'm not going to have you memorize like too many chemical formulas. Maybe some of the ones that we see regularly. If we did like a mineralogy course, you would learn a lot more detail about those things. But just know that they can be expressed in that chemical formula. Next up, we're asked, what is a rock? So a rock is an aggregate of minerals. So by definition, typically rocks contain more than one mineral. However, some rocks do contain just primarily one. Limestone rock forms from calcite. It's pretty much just calcite. But other rocks are going to form with a combination of different minerals. All right, some of them can also contain mineral-like materials. So things like coal or obsidian and pumice, which are volcanic glasses. Those could be considered rocks or be parts of rocks, even though, again, they're not truly minerals themselves.
Well, what about things like chalk?
Chalk is a mineral or a rock, usually a rock, depending on what kind you're talking about. All right, so then it becomes, how do minerals form? So there's three main ways in which minerals form. The first is precipitation, the second is crystallization, and then lastly is deposition. So these are the three main ways in which minerals form. We're going to talk through each one. Precipitation occurs when salts form, when you have water with ions that is going to reach saturation. It can do this for one of two ways. Either temperatures can drop, which means that the water can't hold as much material as it used to, so things precipitate out, or water could get removed. Maybe evaporation occurs, some water is removed from the system. Now whatever is left is not enough to keep all of those ions dissolved, so they precipitate out of solution. Ions in this case are going to bond to form crystalline solids. This can occur within the pore spaces of rocks, which would create like geodes. If you've ever seen like a rock that you crack open, it has crystals inside or salts inside. That would be this process occurring.
I happen to know that, you know the walkways that are like raised outside?
Yeah.
There are some stalactites forming underneath them.
Yeah, you can see them. I think probably because I think the pool is up there. I don't know why at this school the pool's not on the ground floor. I've never heard of a pool being on a second floor before, but I think it is here. And I feel as though it's possible maybe some of the water seeps through there, and then the salt in the, like the chlorine salt in the water of the pool could be responsible for forming that. So if you have ever done like a grow your own crystals kit at home, like maybe you were a kid and you did that like grow a crystal, or if you've ever made rock candy at home, that's like this process in action. So usually with those kits, you like super saturate a solution and then you sit it in a window and you leave it for a few days and you come back and like some crystals have grown because whatever was in there, the water eventually evaporated and the stuff started to precipitate out. So that's an example of how these would form. with rock candy, you just do it with like a bunch of sugar. And these are some examples. So we have some salt flats on the top there that if the salt is being mined off the salt flats, it just forms like a crust on the lake bed or whatever we're looking at.
And the other one is amethyst.
Yep, this is an amethyst crystal, or an amethyst geode. Amethyst is a form of quartz. It's purple in color. Now the next one is crystallization of magma. This is how a lot of minerals are formed, especially a lot of the ones we're going to discuss. Our most common rock forming minerals primarily form in this process, crystallization from magma. So when magma cools, ions within it begin to bond to one another. Crystallization of a molten mass gives us igneous rock, where individual mineral crystals are intergrown and lack well-developed faces. So igneous rocks are going to be comprised of a combination of minerals, and they're going to kind of intergrow and interlock together, usually creating like a speckled appearance in the rock if it has a texture that allows us to see the mineral grains, or if you were to like use a microscope or like a mass spectrometer, you'd be able to see that there are a lot of different minerals in it, even if you can't discern each one individually with the naked eye. But a lot of times you can discern them with the naked eye. So in New Jersey, we have a lot of granite. Granite's like one of the most common rocks on Earth. It's the primary constituent of continental crust. It's a really sturdy rock. It's hard, it's heat resistant, it's great for countertops, right? Because this is forged in volcanoes, so these bad boys, they're used to hot temperatures. It's like you can put your pots and pans on them, they're not gonna burn your countertops. They're very sturdy. What is granite comprised of? It's made of all these different types of minerals that we're gonna talk about. When you look at granite, it typically has a speckled appearance like this. Sometimes it's more pinkish in color. This one's kind of a more cream color. But when you look at a sample of granite, you can sort of discern the different minerals with your naked eye. So the kind of pink, or kind of, sometimes they're like orangey pink or salmon pink, that's what we know, that's a type of feldspar, which is the most common mineral on Earth, when you combine the two feldspars. There's also feldspars that can be a more white or gray color. So that's kind of like some of the big crystals that you'll see in granite are going to be your feldspars. Then we have our quartz crystals. These tend to be like transparent or at least translucent, so you can kind of like see through them into the rock itself. That would be our quartz. It typically has some kind of blobby shape to it. And then we have speckles of darker minerals, which are going to be a few different things. If the dark mineral is like very iridescent and sparkly, it's most likely a biotype mica. If it's more matte black or really dark gray, it's probably something called a hornblende or an they're a mix of these two mineral groups called amphiboles and pyroxenes, which are very similar in their chemical composition, but they're just going to create the darker matte black colors that we see. So this is an example of granite from South Carolina, but you probably see granite. I would be amazed if someone here hadn't seen granite before. It's a very common rock, and like I said, we use it in our countertops and our kitchens and bathrooms a lot as well. Now, the last way in which a mineral can form is through the process of deposition through biological processes. Even though we said that minerals don't come from organic processes, we said, oh well, but there's some exceptions. So there are certain animals that live in the ocean, and they draw ions in from the seawater, and then they use it to help build their shells. And that can either be shells of calcite or shells of silica, depending on what the organism is. When these animals die, their bodies sink to the bottom of the seafloor. They group up together, and then they lithify into a solid mass, which would be the mineral containing one of these types of chemical combinations. So calcite can form from the shells of things like mollusks and coral, and then these other animals or little creatures called radiolarian and diatoms, they have silica skeletons that they're created from quartz. So when they die and the quartz forms together, it forms something called a siliceous ooze, and then it can form into quartz itself. These form what's called a calcareous ooze when they all come together and lithify into one sample. So that's the last way that they can form. This next picture shows you some examples skeletons of radiolarian on the top, so those are little quartz skeletons. They're really small, so you need a microscope or at least a really strong magnifying glass to see them. And then these are some mollusks on the bottom, just some standard clams. So again, a seashell by itself wouldn't be a mineral, but if enough of them get together and form like one cohesive unit of mineral material, then it would be a mineral. So it's a little hazy, but just kind of see what it looks like, and then you figure out if it's a mineral or not. All right, so any questions on formation of minerals? Okay. So what we're gonna move on to now are the properties by which the properties that we use to determine a mineral sample's identity when we're presented with that mineral sample. And this is what you'll be doing in your lab. So you wanna make sure you know how to perform these tests and what to look for. So these are some different properties that we use. We're gonna go through each one. But just like if you were looking at anything, your brain is gonna automatically process some information about it to figure out what it is. Properties that we look at for minerals include luster, the ability to transmit light, the color of the mineral, the streak of the mineral, its crystal shape, which is also called its habit, its hardness, whether or not it cleaves or fractures. If it has something like tenacity, we look at its specific gravity, and then we look at some other special properties as well, because some minerals have really distinct properties that make them easy to recognize.
Like if they're magnetic or something.
Yep, magnetic, effervescent, all kinds of things. So the first one we look at is luster. And to simply put it, luster is the way in which a mineral reflects light. So how would you observe the luster of a mineral sample? You're gonna look at it under light and say, what does this look like? And describe what it looks like that mineral might feel like. It's not what it actually feels like, it's just like what it looks like it would feel like. So how is it reflecting light? Now, one of the most common types of mineral lusters that's very easy to identify would be a metallic luster. If you pick up a mineral sample and it looks like metal, it has a metallic luster. If it doesn't look like metal and it looks like a rock or something else, then it probably doesn't have a metallic luster. It's usually pretty easy to tell if something has a metallic luster because like you'd literally be like, oh, it's a piece of metal that I'm picking up. It looks just like metal. It looks shiny like aluminum or whatever it might be. Other lusters include adamantine or a brilliant luster, which is like the luster that a cut diamond would have. So if you have like a diamond ring and it's sparkly, that would be an adamantine luster, a brilliant luster. Some might have a greasy luster. Again, it doesn't mean they feel greasy, but they just look like they would feel really greasy. So if they look greasy, they have a greasy luster. Something like earthy, kind of just looks like dirt. Sometimes it's described as like a dull luster. Waxy is gonna look like a big chunk of wax. Silky, pearly, kind of self-explanatory. And then the last one is called vitreous, which is a glassy texture. So if it looks like glass, then it has a vitreous luster. So there's some examples here on this next slide. They're kind of hard to see. It'll be easier when we want to see these in person, but I think you can get a sense. So on the left there we have metallic. There is also this category of submetallic. So if it kind of looks like a rock, but kind of looks like metal, something like this would have a submetallic luster. This one's kind of hard to tell, but you could imagine if it like looked pearly under the lights. A brilliant luster, resinous and vitreous. Here's a greasy one, earthy, silky. So really just like if you were shown this sample, how would you describe its appearance? That's probably its luster. Okay. And again, it's pretty subjective, but there are definitely answers that are wrong. But there are, you could argue a few for one mineral sample, and it doesn't mean one person's wrong. Another thing we look at is the ability to transmit light. Now, these are two terms that I hear confused a lot, translucent and transparent. So if you want to jot down the definitions of those, you can use them appropriately. An opaque substance is not going to transmit any light. So it's not see-through at all, it's solid, you can't look through it. A translucent substance is able to transmit some light so that you can sort of see that there's light coming through it, but it's not clear enough for you to see an image through it. So like frosted glass, that would be like translucent. I can see the light coming through, but I can't discern what's behind it. And then something that is transparent is completely see-through, so both light and images are transmitted through. So you could look right through it, like your glasses or, this quartz, whatever it is that you're looking at. So that would be our next property. Next up is color. So some minerals have characteristic colors that make them easy to identify, like pyrite is kind of brassy gold color. Sulfur is like bright yellow. But color is really not that reliable for a couple of reasons. First off, some minerals come in a wide array of colors, and a slight change in their chemical composition can drastically change their color. So when you look at a mineral and you're like, okay, well, this mineral hits 10 of the 12 criteria to be, like this sample matches with 10 of the 12 criteria for, choice A, but it says that choice A is brown and this looks more red to me. Okay, well then just go with that because color is not that reliable. Colors can change, they can come in a lot of different colors, and there can be a lot of variation in the color of a specific mineral. So I wouldn't ever use color as your deciding factor on what mineral you're looking at. You can use it as a supporting factor, but even if it's a color you don't anticipate, if it matches a lot of other criteria for a specific choice, I would go with that choice. Because it's just not really that reliable. The other thing that's good about colors is it's very easy to identify. You just look at it, you can easily tell the color. But again, the reason is that it doesn't tell us much about the mineral. So for example, quartz itself, it's meant to be transparent. So pure quartz is going to be see-through, transparent. However, different additions of different chemicals or impurities can change the color of quartz. So quartz comes naturally in many different varieties. You can have it sort of this white color, which we call milky quartz. It can come in this purple color, which we call amethyst. It can come in this dark gray or black color, which we call smoky quartz. It can come in this pinkish color, which we call rose quartz. They're all the same thing, they're all quartz, but they're all different colors. So if you were like, oh, I think this is quartz, but quartz has to be clear. No, it doesn't. It should be, but it's not.
I kind of watched a lot of Steven Universe, so I kind of got the gist of like what gems are what.
Now you know, right? So something else that we can use that's a little bit more reliable than color is called streak. And streak is the color of a mineral's powder. So sometimes a mineral's streak is different than the color of the mineral itself. And typically streak is a much better characteristic to use to define a mineral than color would be. So you can test for streak by taking the mineral and scratching it against an unglazed porcelain plate. That's called a streak plate. And if you have two samples with the same color, testing their streak can help you tell them apart. So you're gonna do this in the lab. You're gonna get a little tile. It's just a little piece of porcelain. You're gonna take the mineral, you're gonna scratch it along, and you're gonna observe the streak. Kind of like whatever mark it leaves behind. I hate doing streak tests. Personally, it gives me like the heebie-jeebies because it feels really, I don't like how it feels when you grind the mineral onto the porcelain plate, but that's how the test is performed. So you'll do that on Monday.
Maybe sometimes like the sound.
It's not a pleasant experience for me. This is an example of a streak test. So here you can see that we have, on the left, we have this green mineral and it has a green streak. So that's kind of makes sense. Here we have three minerals that have similar colors. Like this one is a little reddish, but if you hadn't seen the streak and you'd just seen these three minerals, you'd be like, okay, they all like kind of dark gray to brown to black. But this one has a red streak, this guy has a white streak, this one has a black streak. So that can help us distinguish more easily than just something like color.
I think that red one might have a little copper or iron in it.
Yeah, we'll have to see. All right, now our next characteristic is crystal shape, also known as habit. So crystals, when they are given enough time and space to grow, minerals will form into their crystal shape. However, most mineral samples that we observe are overcrowded, so they don't actually develop well-formed crystals. But there are all different types of crystal structures. The ones that we see here, we see hexagonal crystal structure here, we see a cubic crystal structure here, and here we see a real fancy one, a dodecahedral crystal structure, so 12-sided crystal structure. I remember as a child, it's so silly, but I remember as a little kid, sometimes I would like take my hand and I would press it into salt on the table, and I would look at all the little salt crystals. And I would be like, I wonder how they cut them into such perfect little squares, right? Well, lo and behold, they don't. That's just naturally how salt forms. Salt has a cubic crystal structure, so when you break a big chunk of salt, it breaks into that shape. Or when salt forms on its own, it grows in that shape. Just like how when snowflakes form, they form a beautiful fractal pattern, right? So they just grow into these interesting shapes. Same thing here. Like I thought, oh, every time you found a crystal like this, I assumed it was like cut and polished. No, that's just how they grow, given enough space to grow. That guy over there, that's garnet. If you're a January baby like me, that's your birthstone. And that grows in that dodecahedral shape, which is just pretty cool. We'll probably see some of it, probably not in the mineral lab, but when we look at metamorphic rock, there's a metamorphic rock in which garnet is very common. So we'll probably see little garnet crystals in that rock. So maybe you'll see their little dodecahedral shape. All right, so should really say 7 major crystal systems, but whatever. Crystal form is the visible expression of a mineral's internal arrangement of atoms, and there's actually 7 major systems, which there are 7 there. I accidentally wrote 6, I guess. Cubic, tetragonal, monoclinic, triclinic, hexagonal, orthorhombic, and rhombohedral. Now, I am not, again, going to expect you to memorize all the crystal structures. If you were doing a mineralogy course, you would know more about this. This is sort of just a for your information. So what are the different structures? It depends on the number of faces and the angles at which those faces meet, and that's going to determine your crystal structure. So this is an example. They go from increasing symmetry to lower symmetry on the side here. So first, sometimes this is known as isometric or cubic shape. So here we have just literally a cube. So A and B and C are all equal to each other, and they meet at a 90-degree angles. Hexagonal is in the shape of a hexagon. Tetragonal is like this rectangular shape where A equals B, but they're not the same as C. And they meet at 90-degree angles. Then we have our rhombohedral. A and B and C are all the same size, but they meet at angles other than 90 degrees. Orthorhombic, they meet at 90-degree angles, but they're all different sizes. Monoclinic, all different sizes, and some of them meet at 90 degrees, but the others don't. And then in a triclinic, all different sizes, and none of them meet at 90 degrees. So it just gives you an idea of what these different crystals would look like. So again, something that you can use as like an additional point when you're trying to establish the identity of a mineral. But again, not all mineral samples express their crystal habit. A lot of times they don't. They'll form in what's known as their massive form, where you won't actually see the individual crystals. Crystals need space and time to grow. And that's what this kind of sums up. So to develop a crystal with well-formed faces, the mineral has to have time to develop slowly and without space restrictions. This normally doesn't happen because minerals are jostling for space. Crowding results in an intergrown mass of tiny crystals, none of which actually shows its form. So the example here would be a massive form of quartz versus a quartz crystal. Both are quartz. More commonly, it's going to be found like that lump on the left, but if it were given time and space, the crystal on the right would have grown. Next one that we're going to talk about is another property that you will test in your lab. This is hardness. So hardness is defined as a mineral's resistance to being scratched. So there is something known as the Mohs hardness scale, which consists of 10 minerals, which are arranged from the softest to the hardest. So our friend quartz, pretty hard, that's a 7 on the Mohs scale. Something like graphite, it's like a 2 on the Mohs scale, pretty soft. If you've ever used graphite, like if you were a Cub Scout, yeah, you use it in your pencils, or if you're a Cub Scout, sometimes they use graphite to like grease the wheels of your Pine Derby cars, your Pinewood Derby cars, because it's soft, so you can kind of like break it apart. The softest mineral is talc, which is like what we use to make baby powder. You can hold it and just scratch it and it will fall apart in your hands, basically. Hardest mineral being diamond, of course. Now,
but unfortunately, talcum powder is also carcinogenic.
Right, well it can be, now we know. So harder minerals are going to scratch softer ones, but not the other way around. So when we're performing a hardness test, it's very high tech. This is what we do. We pick up a mineral, we take something that we know how hard it is, like our fingernail or a penny, and we try to scratch the mineral. And if the mineral gets scratched, then the mineral is softer than whatever that object is. If the mineral does not get scratched, then the mineral is harder than that object. Then we move to another object with known hardness that's a little bit higher, maybe like a nail, like a carpentry nail. and we scratch it again. It still doesn't get scratched. We're like, okay, that thing's harder than a 5.5 on the Mohs hardness scale, and we leave it at that. So it's really basically pretty simple. You're just going to be picking up stuff and scratching it with other stuff and seeing what happens. So that is the hardness test that you will complete on Monday. So make sure you know how to do that. And then we're going to write it up in our lab, and we're going to explain it to someone who never had heard of how to do such a thing. All right. So something like your fingernail typically has a hardness of about 2.5. A copper penny is about 3.5. A knife blade, which we're not going to use in class because it just seems dangerous, would be about a 5.1. Something like a nail or a glass plate are going to have a hardness of 5.5, and the street plate will have a hardness of about 6.5. So we can see if those things scratch our samples. This next slide is the Mohs hardness scale. So at the top there we have our lowest value for talc. Gypsum is 2. They use gypsum in like drywall, like plaster.
Concrete.
Yep, and then concrete. Calcite, we just mentioned earlier, that's a 3. Fluorite, very similar. 4. Apatite at a 5. Feldspar, our most common mineral, at a 6. Quartz at a 7. Main constituents of granite, this is pretty hard rock because it's made of pretty hard minerals. Topaz is an 8. Corundum, this is rubies and sapphires, so they're a 9. They make for good jewelry because they're durable. And then diamond at a 10. Hardest substance on earth, can only be scratched by other diamonds. Okay. Again, good for jewelry because it's nice and durable because it doesn't get scratched if you bump into things. All right, the next property we look at is something called cleavage. So this one's kind of hard to conceptualize until you see it in the lab. So I'm going to explain it to you the best I can, but when we do it, it's something that the more you practice, the better you'll get at recognizing it. But it can be kind of hard to conceptualize. Cleavage is the tendency for a mineral to break along flat, even surfaces. So when you have a mineral and you like smash it or break it, if it creates flat, parallel surfaces, that would be expressing cleavage. A set of faces, parallel faces, that would be one plane of cleavage. So if you have a parallel surface, 2 parallel faces on 2 sides of the mineral, that's one plane of cleavage. If you have a second set, that would be 2 planes of cleavage. And if you have a third, you could have 3 planes of cleavage. So typically most minerals don't express perfect cleavage in all directions, but sometimes there are examples that do. The reason that it happens is because of the organization of the crystals internally. Some of the structures of the arrangement of atoms, it's going to essentially have like weak spots. So when you break it, it's going to break along those weak spots versus breaking across them, if that makes sense. So like some might have like a layered structure. So when you break it, the layers are going to fall apart instead of ripping in half. So that would be something that we would observe in cleavage. One very famous example would be the mineral mica. It cleaves in perfect cleavage in one direction. So this is mica, and when you see the sample in the lab, it literally looks almost like camera film stacked on top of itself. You can just peel layers right off. Don't, because it's annoying and then I don't have any more mica to use, but you can just peel them right off, and it's perfectly flat right across. Other things can have like a cleavage in 3 directions to get that cubic shape. This has cleavage in 2 directions. So see how parallel these are and how flat? They also typically reflect light in a little bit more of like a shiny luster because they are so flat. And then something like this obviously are not parallel, these surfaces, so these would not have cleavage, but in this direction it definitely does.
Something like bismuth crystals.
Yes. They can form into like a cubic. Alright, so cleavage surfaces with their own orientation are counted as a different direction. Parallel surfaces count as 1. Angles at which the surfaces count can also be reported, so if you want to specify even further, you can. These are some examples. So like I told you, mica, on the left there we have what's called a muscovite mica. It's a light colored mica. You can see the layering and you see how well you peel it up. So here and on the bottom, perfect plane of cleavage, perfectly parallel layer. Something like feldspar cleaves in 2 directions. So the top and bottom of this one and these 2 sides. It almost looks like a perfect rectangle, except it's pretty lumpy over here on these edges. So that third one doesn't express cleavage because if I put my hands on them, they're not going to be lined up parallel. and they're not flat. But if I put my hand here and on the bottom, it's going to be very parallel. Halite cleaves in 3 directions at 90 degrees. That's our table salt. So all those little cubes I used to look at on my finger being like, how'd they cut them like that? They didn't. That's just how they break. And then calcite cleaves in 3 directions, but with a 120-degree angle. So more of like a rhombus shape, parallelogram, not a cube like those. All right. Okay, and you can see the hammer there. So literally just smash it with the hammer. But we're not going to do that in the lab because we only have so many samples, so we're not going to destroy them, but some of them will already express cleavage. Now, if a mineral does not express cleavage, it has what we know as fracture. So any mineral that does not express cleavage would be said to have fracture. And again, we can describe the fracture based on its appearance. It's just the uneven breakage of a mineral. For example, quartz has strong bonds in all directions, so instead of cleaving, it fractures. It has a particular type of fracture called a conchoidal fracture, which means it kind of breaks into like a bowl shape when it fractures. The best example I can give you, maybe you've seen it or maybe not, if you've ever broken like a beer or wine bottle, and there's like the piece at the bottom that kind of has that caved in shape, that would be an example similar to what conchoidal fracture looks like. It can fracture in other directions too, or other patterns as well. So the top left there, that is obsidian, so that's our conchoidal fracture. You can observe here, kind of this bowl shape, semicircles. This would have what we call like a fibrous fracture, or like a splintery fracture. That's just a description of what it looks like. So like I said, a lot of subjective, a lot of qualitative data when we're evaluating mineral identities. There are a few things that we can quantify with a value, like our hardnesses and our specific gravity, but most of it is qualitative data. So you have to just kind of practice it and you'll get better at it, and then, you know, you'll feel more confident in your answers. Question?
So, is like the difference between like, or the reason why some would fracture and one would cleave, is that to do with like how heavy rounds the crystal structures are?
It's just really about how they're built. So in which direction are the weaknesses? If they're like layered versus a 3-dimensional network, it's like if there's
So
a,
it's all like, it can compensate?
yeah, it depends on like how well it's connected. Like, it's kind of hard for me to think of an example. I feel like there's probably some sort of example, like think about like a Lego tower. Like if I built just a Lego tower of big Legos straight up and it fell, it's gonna obviously just like break into those flat sections. Whereas if I had a Lego made of like a million really small Legos and I dropped it, it's gonna like shatter all over. So something like that, because it just depends on the direction. It's gonna be more random when there's a more connected network. Another property that we can look at is something known as tenacity. This is our resistance to the mineral breaking. So basically, like, how durable is this mineral? Certain descriptors can be provided. Things like halite and fluorite, when they're struck with a hammer, they're gonna shatter. They're brittle, so they're gonna break into a bunch of pieces. Something like gold or copper, they're malleable. So when you hammer them, they don't break, they just sort of reform or stretch out. They're great for like metal, for wiring for that reason, because you can make them really thin, you can make coils, you can make wires. That's what we usually use copper and gold for. They're good in electronics. Gypsum is sectile, so you can kind of cut it into shavings. And then something like mica is elastic, so it has sort of like a flexibility to it. So if you bend it, it will just snap back to its original position. So all of those are kind of ways that we could describe the tenacity of an object. We're not going to do that too much in the lab, but again, that's for your information. The last one, I think, before special properties is density and specific gravity. So again, not something we're going to calculate too much in our lab, but it will be provided for you in the database. The density of a mineral, density itself is an intrinsic property. It's just a measure of mass per unit volume. So how much matter is squeezed into a specific space. When it comes to minerals, we more commonly use specific gravity instead of density. Specific gravity and density are pretty closely related properties. The difference is that instead of measuring mass per unit volume, specific gravity is measured by taking the ratio of a weight of the weight of a volume of a mineral compared to an equal volume of water. So you look at, you have a mineral, you're like, okay, this mineral is 10 grams, or this mineral has a volume of 10 cubic centimeters. I'm going to get 10 cubic centimeters of water, and now I'm going to mass them and see the comparison between the two, and just take that ratio. Most common minerals have specific gravities between 2 and 3. Some of them obviously are going to be have a higher specific gravity if they're more dense, but most commonly about 2 to 3 times the weight of water. Then the last thing is special properties. So like I said, some just have special properties. Like calcite has a double refraction of light, so if you were to look through it, you would see an image reflected back twice. Magnetism is found in certain iron oxides, like there's a mineral called magnetite. It's magnetic because it has a lot of iron in it. Effervescence is when you have a reaction with a weak acid. So sometimes in the lab, if you want, you can ask me like, oh, can we do an acid test on this sample, and I'll drop a little acid on it and we'll see if it reacts. Effervescence is usually very noticeable. So you're gonna see bubbling, you're gonna hear hissing and fizzing, just like if you drop an Alka-Seltzer tablet into some water, that's effervescence. Fluorescence, some of them are gonna glow under UV light, and then also some smells and tastes. So like sulfur has a really distinct like rotten egg smell. It's very commonly known. Tastes, obviously halite is one you've probably all tasted. It's table salt, so you've probably eaten it before. We're not gonna test any tastes in the lab because like don't really advise.
Stupid.
Yeah, it's probably not best to like just randomly be licking minerals, but some of them do have really distinct tastes, which we'll just have to trust that that's true.
I know lapis lazuli has a bad smell to it.
Yeah, some of them are really smelly. All right, so does anyone have any questions on identifying minerals now? So the last part of this lecture is going to be just looking at the actual mineral groups that are present on Earth. So there are a few minerals on Earth that are really common, and they're known as rock-forming minerals. And those are just a couple, some of which we've already mentioned, and we're going to talk about them again. And then there are 9 groups of rock-forming minerals altogether. However, most of the rock-forming minerals on Earth, in fact, most minerals on Earth are silicates. So that is by far the most common group of minerals, the silicates. After that, we have the carbonates, which can be pretty abundant as well, but not as much as the silicates. And then we have some other groups as well, the halides, oxides, phosphates, sulfates, and sulfides. And then we also have something called native elements, which are certain elements that are just minerals. There's nothing added to them, just individual elements. So there are more than 3,500 known, most of the more than 3,500 known minerals are silicates, like I mentioned, because if we look at the Earth's crust and we break it down by mass of what materials it's made out of, it's primarily made of oxygen and silicon. Those are the 2 ingredients that create silicate minerals. You need to have silicon and you need to have oxygen to be a silicate. Silicates are compounds of silicon and oxygen, and they form in this basic building block called the silicon-oxygen tetrahedron, and we can see it here. So it's 1 silicon ion in the center, surrounded by 4 oxygen ions that create a tetrahedron, which is like a pyramid shape. Okay, so it has a point and it has a base with 3 connecting ions. Right? So this is the building block of the silicate minerals, and these tetrahedron can arrange themselves in a variety of patterns to result in different types of crystal structures within all of these silicate minerals. So the most basic that we look at is, well, would just be the single, the isolated tetrahedron. An example would be the mineral olivine. And then we can form into chains, so the tetrahedron can group up into chains. And it can form a single chain or a continuous chain of tetrahedron to give us things like our pyroxenes and our amphiboles, which we'll talk more about. We can form into these continuous sheets, which are going to produce the micas that I described. And then we can also form these more complex 3-dimensional networks, which are going to give us things like quartz and the feldspars. So much more complicated, a little bit stronger, harder to break, more likely to result, again, in fracture than cleavage because of how interconnected they are. These ones are going to have weaker spots, so they're likely to possibly cleave in certain directions. Right, so again, I'm not going to ask you to memorize any of this. because it's a little beyond our scope for this course, but just be aware that the way in which the silicon-oxygen tetrahedron arranges itself is going to determine the crystal structure of that mineral and in turn its identity. Help decide what it is. So now we're going to go through some of our most common silicate minerals. Okay. I don't think I've told you this yet in this course, but I will repeat it a lot. In geology, we tend to have a lot of different terms for the same thing. And you're going to learn this especially in our lecture next week on igneous rock. There tends to be like a lot of different ways to say the same thing. So one example would be ferromagnesian minerals. They're also called these dark silicate minerals. They are formed from a particular type of magma or lava that is known as mafic magma or lava. It's also known as basaltic magma or lava. So all these different names together, but what you need to know is that the ferromagnesian minerals are ones that have a higher level of iron and magnesium. Ferro comes from ferrous, which is the name for iron. That's why it has an Fe on the periodic table. And then magnesium is magnesium. So these minerals are darker in color, and they tend to be more dense because iron and magnesium are denser elements. In geology, we consider green to be a dark color. So when you see green in a mineral sample, it's a dark color. So if you're like, are there dark or light minerals in this? This one's bright green. Okay, it's dark. So just make sure you know that. Now, the non-ferromagnesian or the light silicate minerals are going to have less iron and magnesium. They're going to tend to have more like potassium or calcium. So they're going to be a little bit lighter in color. They're going to be less dense. So these are our two groups. The feldspars, both potassium and plagioclase feldspars, are going to be our most common mineral on Earth. Quartz is going to be another example that follows closely. Muscovite mica would also be an example of a non-ferromagnesian or light silicate mineral. On the flip side, we have our pyroxenes and amphiboles, which have a variety of minerals within, but they're all pretty similar. Biotite mica, it's just like this, only it has more iron and magnesium, so it's darker and more dense than our muscovite mica. And then olivine, which typically has a greenish appearance, is very dense, not as commonly found.
I have to wonder if like certain rock or mineral groups like that might have a little copper in them, which gives them a green hue.
Sometimes they can, not typically these ones, but other ones would. Other common groups that we have on Earth, the carbonates are going to include a carbonate group. So they're going to have this ion, CO3, a negatively charged ion. So like calcite, CaCO3 would be an example. Anytime you see this in the chemical formula, it's a carbonate. Okay. Sulfates, similarly, would have a sulfate group. Phosphates would have a phosphate group. And you can see that some of them, like turquoise here, much more complicated chemical formula. We've got copper, aluminum, potassium, oxygen, hydrogen, and then a little hydrate as well. Okay. Gypsum there, we've got calcium and a sulfate and then some hydrate as well. So those are some other examples. So basically the name of them kind of gives you a clue of what's in their chemical formula. Oxides are going to have an oxide, so O2. Sulfides are going to have S, not a sulfate, so not an SO group, just S. And then halides are going to have either fluorine or chlorine. These are going to be our salts. A lot of times they're called salts. So things like halite, which is CaCl, or like table salt, NaCl would be another example. Native elements, these are ones that, like I said, are just elements from the periodic table that are considered minerals. So gold, copper, silver, platinum, diamond, which is technically just carbon, graphite is also just carbon. So those would be examples. And then mineraloids, I told you these are things that are like minerals, but they're not quite there. So like opals would be an amorphous form of silica. So they're not exactly minerals. This next definition, this is a mineral polymorph. I just said to you that graphite and diamond are both made exclusively of carbon. So what's the difference? It's just the way in which the carbon atoms are arranged. So in graphite, they're arranged in this way, but they have much weaker bonds between the layers than across, so it breaks easily. It's a soft substance. It's a 2 on the Mohs hardness scale. And then we have diamond over there, much more complex linking of all the atoms. The bonds are a lot stronger, so it's harder to break. Hardest mineral that we have. So that one's going to be a 10 on the Mohs hardness scale. But they're both carbon. They're just nothing else, just carbon alone, just in 2 different forms. And that's why they're called polymorphs. It just means many forms. All right, and now to wrap it up, we're going to go through our 5 most common rock-forming minerals. So again, hopefully by now you're like, okay, she's mentioned these ones a few times. Probably I need to know them. You will probably see all 5 of these in your lab this week. Maybe not all 5 of them. You'll definitely see 3 of them. But these are ones that we're going to need to know. The first is feldspars. Together, the alkaline and plagioclase feldspars make up the largest mineral group on Earth. So they're the group of rock-forming tectosilicate minerals which make up as much as 60% of the Earth's crust. They have cleavage in 2 directions at 90 degrees. Their hardness is between 6 and 6.5. So they don't scratch quartz usually. They're slightly softer than quartz. Alkali feldspars are going to be ones that contain either potassium or sodium, and then this chemical formula here. And then plagioclase are going to tend to contain a little bit more calcium than what we would have here. This has potassium and sodium. So sometimes these are called potassium feldspars and plagioclase feldspars, but you can call them alkali feldspars too. So typically they are going to look creamy to white to pink in color. When you pick up a sample of feldspar, it's going to look very much like a rock. Right? It has sort of an earthy texture or an earthy luster. It does have this sort of rectangular shape if it's cleaved in that way. But personally, I don't really think they're anything too special to look at. They're kind of just going to look like a rock. They're going to be like a creamy or white or maybe a light gray color. And they kind of have lines. Like this one, it says exhibit striations. You can see the lines where this one has broken as well. After that, we have quartz. Quartz, we said already, is a hardness of 7. It's a very durable mineral. It comes in a variety of colors, like we see here. We also have other examples of ways in which quartz can form into other minerals like chert, agate, or chalcedony, or jasper. When rocks form, when igneous rocks form, quartz is the last thing to come to crystallize. So it has to have a pretty low temperature. When it's allowed to crystallize in open space, it commonly forms hexagonal crystals. They're highly prized. People love to use their crystals for whatever mystical properties they might contain. And I don't know if that can be proven scientifically, but people seem to really enjoy them, so that's good for us.
Some people like making jewelry out of them.
Sure, yeah. And they can scratch glass and feldspars because they're pretty hard, so it's just a durable thing. Normally, they're translucent to transparent, and they have a conchoidal fracture. So there's all different examples of quartz. When I was a kid, where I grew up in my town, they were building, I grew up in a rural part of New Jersey in Sussex County, and they were building a new landfill, and then halfway through the project, they lost funding, so they just stopped building it. So we just had this giant hole in our neighborhood that was supposed to be turned into a dump, but they never finished. We called it the sand pit because it was literally just a big pit of sand, and we would go there and we'd ride our bikes because it had all these hills and stuff. The amount of quartz I found in that pit was insane. I would just go and I'd scoop up some sand, and there'd be a big chunk of quartz in there. There's a lot of quartz in New Jersey. It's all over.
You could go panning.
You can find it all over. There's this place in New York called the Herkimer Diamond Mine, and it's known for having really good samples of quartz that are super sparkly, and so they're known as Herkimer diamonds. They're not actually diamonds, it's quartz, but it's just a fun place you can go and get really good quartz samples.
At Cape May, some the round sandstones will wash up on the shore, and they'll be so clear they call them Cape May diamonds.
Yeah, same idea. The next most common are our micas. Mica, to me, is a very cool mineral. It's fun to play with. It's fun to pull apart. It's really sparkly. It's pretty. We use it in makeup. If you ever use a glittery eyeshadow or glittery nail polish, it's a good likelihood it has mica in it to give that glittery appearance. So it's pretty, it looks nice, it's interesting, it's a common one. It's pretty soft, but again, it has that weird cleavage in one direction. So when you don't really like break it, it has that elasticity. You'll see when we look at it in the lab. Very similar to like the feel and look of film. I don't know if you guys have ever used film before. Maybe, maybe not.
I mean, some of us know what a camera looks like.
Sure, I mean, it's like film is not commonly used these days, but if you ever used film, that is really the best way to describe it, or anything that has that same texture. Even like laminated paper, honestly. If you've laminated a piece of paper or a card, that's very much what mica feels like. So it's a kind of a cool one to look at. And then the next one is going to be, this is just an example of them peeling off some biotite micas. Very cool. The last two are going to be the amphiboles and pyroxenes. Now these are very similar. So you're going to see, okay, amphiboles typically are black with shiny elongated crystals with cleavage. And it says right there, difficult to tell from pyroxenes. So like, I wouldn't ever tell you, well, is this an amphibole or is it a pyroxene? If you tell me, oh, it's an amphibole or pyroxene, I'm like, okay, that's fine. Like, they're basically not exactly interchangeable, but for our purposes, interchangeable. They're pretty similar to one another. Look at their hardness, 5 to 6.0. They come in orthorhombic or monoclinic. They're black in color. Here's pyroxenes, hardness of 5 to 6.5. Usually dark in color, like black or green. Hard to tell apart from amphiboles. Also come in monoclinic and orthorhombic crystal structure. So basically the same, right? Okay, so that is all I have for you tonight on our lecture on minerals. Does anyone have any questions for me before we head out in the next 10 minutes or so? Yeah, Chris.
So there was something I missed when I saw on the beginning of the slide. So like a lab-grown diamond does not count as a mineral because it did not
Lab generated. Yeah, so it kind of talks about like, I actually don't know if, so like when I was in school, lab-grown diamonds weren't a thing, right? Like they're new. So I don't really know exactly where they would draw that line now because those are diamonds.
Yeah, that's it.
But it's tricky to say. So I know like typically probably they wouldn't be considered because like a lab-grown sapphire typically isn't considered a mineral. But you wouldn't know unless you knew where that thing came from.
The process itself isn't synthetic. It's
Right.
like just controlled.
Just human,
Yeah.
human driven, yeah. But one quick piece of trivia knowledge that you can use is that by our 5-part definition, technically ice is a mineral because it's a solid, inorganic crystal structure, naturally occurring, and has a definite chemical composition. So if you ever want to trick someone, you can ask them, is ice a mineral? And the answer is yes, technically it is. Until it melts, and then it's not a mineral anymore. Any other questions?
What
Okay.
about the state in between? What if it's like currently melting?
Well, the water part is water, and the ice part is mineral. And if you ask me if it's